Okay, we're going to wrap up our discussion of the residuals with the rest of the output that we got from our analysis with the simple regression case, where again we regressed GPA on GRE Quant. And so you can see the ANOVA table here. We have our sum of squares residual. Remember what we saw, it was 6.5. And the degrees of freedom, I haven't explained those yet, but basically the degrees of freedom for regression is the number of predictors in the model, so that's 1 in this case. And the residual is the total n size, so that's 30, minus the number of predictors in the model, which is 1, and then minus another 1. So it's n minus k, which k is equal to the number of predictors, and that's 1, and then minus 1. So residual df is equal to n minus k minus 1, and then the total df is just n minus 1, which is 30 minus 1. So that's where we get that. All right, so remember that in ANOVA we had the sum of squares divided by the degrees of freedom is equal to the mean square. And so we have that for both. We have, our regression sum of squares is 3.89 something. We divide that by 1, and the mean square is, of course, 3.9. For the sum of squares residuals, same thing. We take the 6.5 and divide by 28, and we get 0.233. And then we divide 2.33 into 3.89. Anyway, you remember this from ANOVA, I'm sure. And then you get that F that's highlighted in blue there, the F test. And so remember, the F test is simply the effect over the unexplained variance, basically. So it's the explained variance over what's unexplained, kind of. I mean, that's a good way to just kind of think about it conceptually. And so we see here that it is significant. So that makes sense. We have a 0.61 correlation, and it was significant, so we should have a significant F test also. Okay, so just one more thing here. We have the standard error of the estimate. And remember, that was in our model summary box along with our R and our R squared. And that was 0.483, and that represents the standard deviation of the distribution of residuals. So we want that standard deviation to be very small, because if it were large, that means that our residuals are very variable in their size, meaning that we don't have a very good predictive model in that case. So just know that the mean square residual and the standard error of the estimate are related, and they both are an index of the error in our model. And of course, the higher the error, the less chance that we have of getting a significant F value. As you can see, when you look at the formula for F, thinking about the numerator and denominator, if you're increasing that denominator without doing anything to the numerator, then you're going to have a small final outcome. So just think about that and kind of picture it mentally of what's going on. All right, so if we take the square root of the mean square error, we get that standard standard error of the estimate. That's kind of like square rooting the variance and getting the SD. It's kind of like that. And so we have the same kind of pattern here with the error in our model. All right, so we have, if you can do the math for that and just see that it all works, and that kind of demystifies the process for you and hopefully makes sense. For understanding this thoroughly for exams and quizzes, I want you to know this ANOVA table like the back of your hand. All right, so you know exactly what each part represents and what makes a healthy F versus a not so healthy F, and what would it take to raise the F value so that it would get significant. All of these things is really, they're all really important to understanding regression, and also just stats in general. I think a lot of these principles apply when we talk about the effect over the error, and the proportion of explained to unexplained, proportion of explained to total variance, all those kinds of things are helpful for understanding the full picture conceptually. All right, so again, the larger the standard error of the estimate, which is the variability of the residuals, the normal curve of residuals, it just gets flatter and it gets wider, so there's more spread of residuals. And the residuals, when there's lots of variability in those, it's not good because it means the points are dispersed around the best fitting line in these unpredictable patterns and ways. And so, again, they're not adhering closely to the line like we would like. And so the higher the SEE, the less likely they are to be nice and tight and hugging and loving that best fitting line like we would like them to. All right, so one more formula for the standard error of the estimate. If we take the standard deviation of our outcome variable, in this case GPA, and we multiplied it by the square root of 1 minus r squared, we would get that same value. So you can do that if you like, just to see that it works. It's just another way of getting at the standard error of the estimate.